A very good evening to everyone. It is my pleasure to welcome you all for our virtual seminar on emerging trends in nano energy and nanoelectronics. Today, we have four eminent speakers from Amrita who will enlighten us about the current trends in the field of nano energy and electronics, and also a successful alumnus from Hindustan Petroleum Corporation Limited, India, Bangalore, who will briefly share her experience here at Amrita. To begin with, our first speaker is Dr. Shantikumar V. Nair, who is the Dean and Head of Research at Amrita, Faridabad campus in the Delhi NCR area, and also in the Kochi Healthcare campus in Kerala, which is a part of Amrita Vishwavidyapeetham. Today, Dr. Shantikumar V. Nair has a PhD in material science and has been working in the area of biomedical technologies for the last 15 years. He is the fifth ranked material scientist in India and has an H index of 87. He was a professor at the University of Massachusetts, USA for 20 years before coming to India to establish a program in medical diagnostics and therapeutics using advanced technologies. He has been conducting research and teaching students for the past 15 years in Amrita. I now invite Dr. Nair to start the seminar.
Introduction using a few slides to give you an overview of nanoelectronics and nanoengineering. So we'll just wait for the first slide. Hopefully you can see that first slide. So you go to the first slide. So one of the exciting things that has happened in India in the last decade is that there is a new ecosystem in nanoengineering and nanoelectronics involving a lot of innovative research and development. Some of the areas that have been focused on, which successfully in India, is nanomaterials, nanoenergy, nanoelectronics, nanotechnology in water purification and other purification processes, nanotextiles, application of nanotechnology in agriculture, and of course, application of nanotechnology in the medical area. So these areas have had a tremendous impact in India. And the program that we are talking about today is focused a little bit less on the medical side and more on the engineering and electronics side. So what has driven this new innovative ecosystem is the development in the industrial sector of nanoengineering and nanoelectronics. There are not only established companies, but a lot of startup companies as well. Over 100 nanotech startups have focusing exclusively on the engineering side of nanotechnology applications. And if you look at established companies in electronics and engineering, there are about 700. So per month, we are looking at hiring of professionals in the range of 1,000 to 5,000 all over India. So as I had said before, whereas earlier, maybe a couple of decades ago, we had been focusing on importing technologies and trading technologies. Now we are focusing on developing our own technologies and devices in India. So India now, and this is quite an impressive number, is manufacturing its own electronics and engineering devices and products to the tune of about 6% of all the global electronics and engineering output, which is quite impressive. And that is fueling a lot of more R&D work and a need for trained manpower in this area. So what does a student need to do in order to understand this new, rapidly developing electronics and engineering ecosystem? What kind of exposure do they need? And that's what we have been studying for a while, and the kind of exposure we are providing. So one is knowledge of nanoscale materials, manufacturing at the nanoscale, interaction of electronics with materials and scale, electrochemistry, and also bioelectronics, which is a field where biology and electronics are coming together for many wearable electronic devices for the healthcare sector. So what is required here in this new area to develop your career in this area is an interdisciplinary exposure. So the field is at the interface of several disciplines. One is the interface of engineering, electronics, and materials. The second is the interface of biology, engineering, and electronics. And the third is the interface of chemistry and electronics for advanced product development. So these areas are areas where we will be providing a lot of training in our programs here. And it's very important to get into the sector. So if you look at the next slide, what are the career opportunities that students can expect? So one is advanced engineering companies. Many engineering companies are almost quite at an advanced level, looking at nano applications in the engineering sector. Nano is an enabling technology, and almost every engineering department is looking at nanotechnology applications. There are a lot of startups that have started, as I said, there are over 100 of them, and those are good career opportunities. Electronics companies, nanotech companies, research institutions, that includes in the government sector as well as in the private sector, and a lot of international opportunities. The development of nanoelectronics and engineering is much more so in the Western countries than it is so far in India. And so opportunities to get an international exposure is substantial. So I will close with a little bit of background about Amrita Vishwavidyapeetham. So we are actually today an 8-campus system with 20,000 students and 2,000 faculty. We are ranked in the top 10 among all universities in India, and we are a NAC A++ grade university. So the program that I would like to introduce, if we go to the next slide, is the program that is held in Kochi, which is the Center for Nanoenergy and Nanoelectronics and Nanoengineering, where we have a program both at the master's level and the PhD level. So some of the innovation products that Amrita has pioneered, and all of these are work that has happened here in Kochi at our Nanotechnology Center. One is high power lithium-ion batteries, recycling of electronic products, solid-state batteries, and photonic applications such as sensors and detection of diseases, where we can avoid a biopsy. Next slide. So I will close by saying that I invite you to apply and pursue a career in what is one of the fastest emerging fields in engineering and electronics today. We have 2 programs that are active. One is an M.Sc and the other is an MTech in nanoelectronics and nanoengineering. And both of these programs are offered in Kochi, Kerala. Thank you.
Thank you, Dr. Nair, for your presentation. I now invite Dr. Damodaran Santanagopalan, who is the professor at the Nanoengineering stream of Amrita School of Nanosciences and Molecular Medicine, Kochi. He has made distinguished contributions in the area of designing and engineering of nanomaterials for various energy applications and modifications of materials for biological applications. Dr. Damodaran received his PhD from University of Hyderabad and was a faculty at the physics department in IIT Kanpur. Before joining Amrita, he was a postdoctoral fellow at the Laboratory for Energy Storage and Conversion at the University of California in San Diego. Sir will address about nanoelectronics and nanoengineering at Amrita and the expectations out of this program. I request Dr. Damodaran to take over the session.
So a very good afternoon to all of you. I'll give a brief presentation about what we are doing at Amrita in terms of nanoelectronics and nanoengineering. So, just to introduce, what is nano, and specifically in terms of scales that what we look into day-to-day, life. For example, a mountain, which is typically about a kilometer in height, for example, is 1,000 meters. And compared to that, a child who is only 1 meter in height is coming down 1,000 times. And similarly, when we go down smaller and smaller and 1,000 times every step that we go down from, let's say, a meter to a millimeter to a micrometer, and a single sugar molecule is about 1 nanometers in size. So that's typically what is the size that we are talking about when we talk about nano. So it's not that just that we see these kind of structures into, nanoscale. And, we have nanotechnology in nature as well. So you can see that, for example, we see the lot of, the lotus leaf, which actually the droplet creates an hydrophobic surface because of the, nanoscale structures that has similarly, a lizard's, feet has certain nanostructures, which creates strong van der Waals forces. And you also have these kind of colorful structures in a peacock feather, which is combinations of pigments and nanostructures and photonic crystals, and the butterfly wings, which the way light is getting, manipulated because of the existing micro and nanostructures in these, wings and, the butterfly wings. Also, you might have seen insects which basically float on water is basically based on the buoyant effect because of the hair strands that traps air, between the, hair strands and things like that. That helps the, these are all, day-to-day nature observations that we can see that nanotechnology plays an important role in all these kind of applications. So what makes nanomaterials unique is because of the properties that we are interested in. For example, we are interested in mechanical properties or optical or chemical or physical properties, thermal properties or magnetic properties. We can see that when you look at mechanical properties as an example, right? So you have materials which are really light, but at the same time have very high strength and toughness and elasticity, things like that. So similarly, when you go down to nanoscale, you also have chemical effects like, very high catalytic effect. Or when you look at, physical properties where, melting point of nanomaterials can be completely changed from, let's say, for example, bulk gold has a melting point of about 1,064 degrees Celsius, but when you make it less than 10 nanometers in size, gold nanoparticles, the melting point can go down below 500. Similarly, when you talk about, optical properties of semiconducting materials and quantum dots, you can see very nice quantum effects. So look at the three different colors in those bottles and vials, which is basically same material, but different size effect gives fantastic colors. That's a quantum confinement effect. And similarly, magnetic nanoparticles, which can actually help in have very high magnetic, fields and strength. And similarly, thermal properties also very important when you go for, having a material which has very high thermal expansions and things like that because of the nano size effect. But if you look at nanoelectronic applications, the future is very bright. The picture that you're seeing is basically not an Iron Man suit or an Ant-Man suit. It's basically a normal human suit, which actually has a thermal regulating textile. Because individual person can have different environments, being in an air-conditioned room or outside environment. The temperature can be regulated based on the textile, which is basically based on nanoengineering. And now this kind of textiles are coming up very fast in, developed countries. And similarly, you can have nano sensors or even healthcare applications where you can make devices which is basically, patient friendly. At the same time, you can also have different kind of sensors attached to, humans in terms of patches or, stickers, which basically monitor human health. At the same time, you can also see nano devices which are useful in Internet of Things, where you can sit at a particular location and control devices. That's actually another important field that is coming up based on nanoelectronics. And you can see that small device which actually can be powered. So there is a micro battery, there is a micro LED, and also a sensoric devices which can actually be integrated onto a single step, where it could be a ring or a wristband kind of possibilities of nanoelectronics. When you look at nanoengineering applications, you actually have, for example, piezoelectronics is one of the other attractive field that's coming up. For example, uh, piezoelectronic is basically when you shrink or expand a material, it can produce voltage. So when you are running, your shoes bottoms can be coated with piezoelectric materials, which can generate power, and that can be actually stored to charge your mobile phone or something when you're simply doing a jogging or something. Similarly, water is an important problem for the future because water, purification is one aspect, and treating industrial wastewater to make it, better for the humans is actually another important thing. So nano catalysts are being developed for treating, water waste from the industries. We also have nanoscale devices, sensors, and also batteries that are being printed by 3D printers, because we are not looking at lateral dimensions alone. We also have three-dimensional structures that have to actually be engineered to have better performance for catering the future needs. And we are also looking at solar cells. For example, you see a solar cell here. It is basically, printed on a flexible surface, which basically means that we are not looking at solar cells for outdoor applications, but also for indoor applications, because all the lights inside the rooms are basically, producing some amount of, light that can be absorbed by the solar cells and can produce enough energy. So if you look at in all these lines that I have mentioned, that Amrita is actually at the Nano Center. We are doing research in all these aspects, typically whether it is nano engineering or nanoelectronics. So typically, for example, we develop fast charging lithium-ion batteries, where you can see in the slide where 4 LEDs are lit by a simple coin cell. Similarly, we are also doing, photocatalytic water remediation process. So the first picture that you see on the left has an yellow colored water is basically because of heavy metals. Within 30 minutes, the catalyst can completely reduce the toxic heavy metal to safe conditions, and then this can be filtered and used for further applications. Similarly, we also do nanoelectronic applications, where you see in this particular picture, there is a small single isolated nanowires, which we can actually manipulate to do electrical characteristics and things like that. Simultaneously, we also do engineering of nanomaterials for solar cell applications, which is typically a dye-sensitized solar cell. So you can see that 2 different particle size can have a different absorption intensities, and also, heterostructures and photodetectors, heterostructure-based photodetectors for nanoelectronics and nanoengineering applications. The important thing about all this is possible because of the expert teaching at Amrita. We have faculty members. I've listed a few of them who would probably be teaching when you join our course. And, typically, for example, Professor Manzoor will be talking about characterization of nanomaterials. Professor Deepti, for example, synthesis of nanomaterials. And Dr. Lakshman, for example, will be talking about VLSI technology and nanoelectronics. And Dr. Sendil will be talking about or teaching you about nanoengineering applications. And myself will be teaching about nano energy and optoelectronics kind of applications, where Professor Nair will be teaching you about, properties of nanomaterials and material science for the future, and courses like that. So one of the important strengths of our center is basically the students have, access and training for their research purposes for all the sophisticated facilities. For example, whether you're looking at the, battery fabrication facility, or electrical measurement facility, or microscopes, or even for the nanoelectronic applications, we have the clean room facilities where you would be knowing the industrial standards and protocols for working in such environments. And also we have applications that are basically based on clean room applications for nanoelectronics. And some of the other facilities for nanoengineering applications that you see on this particular slide, where the students are working with the facilities, or solid state battery fabrication facility, or nanomaterial synthesis facilities, characterization facilities and fabrication facilities, things like that. We also have facilities that are used for nanomaterials. For example, always we talk about surface area as an important property for measuring, that we also have facilities which also, very important to be manufactured. And some of the recent student placements, I just wanted to highlight that some of our previous master's program students have been into, for their higher studies and jobs in different countries. Some of them are highlighted here. For example, United States of America, Australia, Germany, Korea, Middle East, and Netherlands, UK, and Canada, to list a few of countries that our students are around. And one of our important point to mention that is our international, national, and industrial collaborations that we are basically having with. We have going on collaborations with industries like Log9 Materials, Minimine Clean Tech Solutions, or VoltQ Energy, or Full Chain Materials. And also we have collaborations with universities within India and abroad. For example, University of Technology in Taiwan, or UCST. At California and Seoul National University, we have initiated a program on sustainability. IASC, we have collaborations for sodium-ion batteries. Similarly, we have collaborations with DRDO and ICGEB, kind of institutions across India and abroad. And one of the main point that our strength as far as training you is concerned, we have a very good program with hands-on training. We have very focused theory courses. We have time-conscious projects that are guided by experienced faculties. We have very advanced labs. And we also have modern teaching methodologies that we follow, which makes Amrita a unique place for nanoelectronics and nanoengineering applications. So join ACNS empower the future by embracing change with nanotechnology. Wishing you all the best. Looking forward to meeting you in the labs. Welcome. Thank you.
Thank you, Dr. Damodaran, for your presentation. Next, we have our third speaker, Dr. Sendil Kumar Bhaskar, who is the Assistant Professor at the Nanoengineering stream of Amrita School of Nanosciences and Molecular Medicine, Kochi. He received his PhD from Bharatiya University. Prior to joining here, Dr. Sendil Kumar had worked as a postdoctoral research associate at Jawaharlal Nehru Advanced Scientific Research Center in Bengaluru, where he worked on developing electrochemical cells and batteries. He is currently involved actively in government-funded projects in this field. His significant contributions to nanomaterials and energy storage and conversion technology research is well known from his publications in leading journals. Sir will specifically talk about the energy applications of electronics and engineering. Over to you, Dr. Sandhu.
Good afternoon, everyone. So today I'm going to talk about more on the nanoengineering applications. So today I'm going to talk more on the nanoengineering for energy applications. Already Sir showed all the facilities available in our lab, and he also showed our applications in many energy-related applications. So I will only focus on four major components like solar cells, hydrogen production, batteries, and fuel cells. And when we talk about solar cells, the main material used in a solar cell is a semiconductor material. So there, the materials that absorb light and release electrons, that is a semiconductor materials. Mainly, you can see in a solar cell, the silicon is a main material used in a P and N junctions. So that is a very important materials. But currently, how nano is coming to the picture here is making the nanostructures in the silicon materials like a nanowires. Okay, so how the nanowires will be bringing the main part is like when you make a nanowire that can absorb more light, and also you can tune your refractive index of the silicon nanowires, so it will bring more absorption of light. And as well as whenever you go nanostructures, you are reducing your weight of the materials. So you are reducing cost as well as increasing the efficiency. That is also matters in the large scale production of silicon materials for the solar cell applications. And whenever you go to the photoelectrochemical water spreading, that is not a mature technology, but still people are working on the currently people are working in this material because this is a very good field, and where the semiconductor nanomaterials can be used in that. Okay, so I'm going to the hydrogen production. That is a new photoelectrochemical water splitting is a new area of developments happening on that. So here you can see I gave a scheme that is recent work published in the paper. So we can see the nanostructures, how it can be efficiently produced. Previous slide, please. Yeah, how efficiently it can produce the hydrogen vehicle technology. Now you can see the lithium-ion batteries commercialized in 1991. After that, there is a huge market, and there is a developments happening in everywhere, even in electric vehicles. Like you can see, this is got Nobel Prize in the 2019. The three pioneers in the field, John V. Goodenough and Stanley Whittingham and Akira Yoshino, got Nobel Prize for the development of lithium-ion batteries. And you also aware of how lithium-ion battery works, right? So the cathode is made up of LiCO2, the conventional lithium-ion battery, and graphite is the anode. So during your charge, the lithium ions from the cathode structure deintegrate from the structure and deintegrate into the graphite anode, and the electron will be coming up in the outer circuit. So similarly, during the discharge, you can use the stored charge in the battery can be used for the any applications. The reverse process, like lithium coming back to its original position, and the electron in the outer circuit can be coming back. So this is a reverse process, and it is called intercalation mechanism. It can be used for storing the charge. So here, the one important category is nowadays we are using electric vehicles, but the problem is the charging, right? We can charge the battery for in 5 minutes or like that. Whenever you go to the normal oil, petrol or refueling, you will take only 1 or 2 minutes. But in electric vehicle, you need at least half an hour to 1 hour to recharge your batteries. But that is a major problem. So where you need 5 or less than 5 minutes to fast charging. So in that field, we can bring the nanostructures to fast charge your batteries. So one more. Yeah. So the nanomaterials in here play a major role and bring the fast charging capabilities, because the nanostructures have the capability to bring fast charge transfer kinetics, and we can make high power batteries, what Damon sir also showed you. Okay. So another big problem in the electric vehicles is the catch up of fire and the fire hazard. So why the fire hazard is coming up is a liquid based electrolyte used in the conventional lithium ion battery what we are using now, because you can see the liquid electrolyte is a flammable electrolyte. So whenever there is a conditions called high temperature or long cycling dendrite formation, it can also in a long term cycling it can also catch fire in a previous slide, please. So what we can do, what we can for in future we can do, bring the solid state electrolyte. Solid electrolytes can be used in the conventional lithium ion battery. Then you can bring the safe and solid state, all solid state batteries. So you can bring a lot of improvements, like the blue lines. What are the blue highlighted is a positive advantages of the solid state battery, like a high thermal stability, application of next generation cathode, high voltage reliability. So other problem is you can't go in above the high voltage, like a 4.5 volt. You can go in the liquid electrolyte based system, because it is has a homolumo band, so it can go beyond the electrochemical window. Okay. So that's why we are going to the solid state batteries. And what are the nanostructuring and nanoengineering can be bring in the solid state batteries and further improve the performance and safety of the battery. Okay. So even though I said the solid state battery, the solid electrolyte will bring some advantages, but you can see there are some problems also. Whenever you go to the solid-solid interface, there is interface failure problem as well as lithium ion transport problem. So how to bring the nanoengineering to bring the some improvements in this. Yeah. So when you go to the cathode side, there is a problem with the interface failure. So what you can do, we can bring some nanosizing the cathode. Then there you can doing the shortening of carrier transport path, and you are bringing more active sites to participate in the reaction. And whenever you go to the higher voltage, there is a problem of electrolyte and surface having the problem. So when there we can bring the surface coating layers, then it can bring some improvements in the previous slide. So you can bring the nano thickness coating that can also improve your performance. That is in the cathode side. Anode, you can see you can use nano fillers or CNT. You can further improve the softening of lithium ion transport. That will bring your interface problems like lithium ion transport, and it can also suppress your volume strain. So these are all the advantages you can bring with the nano technology. So that is very important for the future developments in the batteries. The next slide. Yeah. So here, the one more example, the final example what I'm going to give is a fuel cell thing. Fuel cell, the important problem is the use of the high cost noble catalyst like a platinum carbon that can be given in anode and cathode. There we are using the high cost platinum as a noble catalyst. So what we can do is we can bring our nanoengineering and nanomaterial things. Then we can also put like a nanostructuring our catalyst, and we can improve the performance. There is one recent report, they are increasing the 30% efficiency, and they reduce the cost of the noble catalyst, and they are increasing the application. So this is also an important field. We can do a lot of things to improve the performance of the batteries. So I think there are many fields, nanotechnology and nanoengineering can do a lot of magic. Okay. So with this, I would like to conclude. Next slide, please. Yeah, so we have a lot of posts already what are discussed. So we have a lot of important posts which can cover these all 4 major areas in the energy field. So people can join in this course, can benefit from these courses, and they can also do some good research in this area. So next slide, please. Yeah. So and as well as I want to highlight one point, like a target of India's 2023 target is like a to achieve 500 gigawatt of renewable energy capacity by 2030, and as well as EV30 at 2030, that is like a 30% of private cars being equipped by the year 2030. So these two targets can be achieved only by then only it can be achieved. And there are a lot of companies in India itself doing in R&D, even batteries as well as solar cells. So there are the future students can get placed in this kind of R&Ds that will be very good for our Indian future. Okay. With this, I would like to thank the participant. Thank you for your kind attention. And this is a slide which shows the IV. Our students went for the IV in the top companies in batteries and as well as recycling, industrial usage. Thank you.
Thank you, Dr. Sendil Kumar, for your presentation. Our next speaker is Dr. Lakshman Raju Tottam, who is the Assistant Professor at the Nanoengineering stream of Amrita School of Nanosciences and Molecular Medicine. Dr. Lakshman received his PhD in nanoscience from Northern Illinois University, USA. His postdoctoral research is based on the synthesis and characterization of high-quality, wide bandgap complex oxide thin films and heterostructures at the University of Minnesota, USA. Currently, his research focuses on nanoelectronics and electronic applications of nanotechnology-based materials for various catalytic applications, solar cells, solar chips, etc. Dr. Lakshman will talk about nanoelectronic applications and its importance. I invite Dr. Lakshman to take over the session.
Very good evening to everyone. We are all talking with nanotechnology, nanoengineering, nanoenergy, nanoelectronics. All the nano terms have been heard for the last 45 minutes. But do you know where it all started? It all started in the year 1959, where the famous scientist Richard Feynman said in his talk, there is plenty of room at the bottom. He did not foresee what is going to happen in the next 60 years. But look at where we are now. Everything you look just around, everything is nano. It's always good to revise things. So I just want to give you one more example of what nano is all about. So on this slide, you can see different pictures that we see in our day-to-day life, like a tennis ball, an ant, a human hair. And you look down, you can look at their physical sizes. A tennis ball is in the terms of centimeters, but I wrote everything in terms of nanometers just to bring that, perspective. A tennis ball is around 100 mega. That please note that capital M is mega and then nanometers. And then the next one is ant, human hair, and then you can get into our blood, DNA, and atom. So atom is at the fundamental level, DNA, RB. So anything which is, of the size of the order of human hair. Okay, when I say human hair, don't be confused here. It is not about the length of the human hair. It is about the width of the human hair. Okay, please be cautious. It is just the width of the human hair that I'm referring to. Anything below this is considered in terms of nano. And this nano can have many applications in many different fields. But I just want to focus here on nanoelectronics and how this has changed into the future. So just to give you a perspective of what we are looking into. So as I'm guessing most of the participants in here are UG students or parents who have a little, hands-on experience on this guy, which is called as a breadboard, where we all played with, playing simple circuits. This is where we all started. We have resistors, capacitors, LEDs, buzzers, and all these things. And if you look at the size of this is typically in terms of hundreds of centimeters where our electronic circuit started. Then the next version came is PCBs, printed circuit boards. What we tried to do is we are just trying to make the same in terms of a smaller size. And you can see from hundreds of centimeters, we came down to tens of centimeters. This is the physical size of the electronic circuit that I'm talking. And then in the printed circuit board, you can notice that there are many blackish, grayish components. And if you take one of that such component, wherein I put, and a simple example is 555 integrated circuit, which is a timer, which is an integrated circuit, and its size is 1 centimeter. Now, if you go further down, we are entering into the actual nanoelectronics and nanoengineering, and which is in the size of nanometers. And here is a famous example of Intel 4004 CPU. Right now, we are at i3s, i5s, i7, but it all started with this guy, which is Intel 4004 CPU, which is the first central processing unit manufactured by Intel. And you just look at this perspective, how small this is. But when you zoom this guy out, when you look into this, when you look into this Intel 4004 CPU, look at the complexity there, look at the maze. It amazes me like how you can design this at this particular scale, and you can see all the interconnections, and this can do all the additions, subtractions, multiplications. And this is in the year like 40 years ago. Now we are at I3, I5, I7. So the complexity has further increased. So to you looked at that maze, right? How amazing it is. But how do you make that? To make that, what we need to know is first and foremost thing, we need to understand the working principles at such a small scale. How does an atom behave? How does a molecule behave? What are the interactions of this? And once you understand those working principles, next we should be in a position to design and tailor each individual atom or molecule as per our requirements to produce a given output. So the first thing is you need to understand them. The second thing is you need to design them. And the third thing is once you have an atom and a molecular understanding at the molecular level, then you need to be in a position to put them together. Because not one atom will give you a circuit, right? You need to have a culmination of materials, circuits, interconnects, all of them to be putting together at such a small scale to give you an output. This is all in simple nanoelectronics. First, we need to understand, design, and then put them together to make it. Now you might ask, sir, where are the applications? You just look around you. Right now we are using Zoom, right? I'm using a computer that is a nanoelectronic. I think some of the students are using mobile phones. It might be Android, Samsung, Zio, or anything. Inside that phone, what is there? A chip. And that chip is made up of nanoelectronics, circuits, and the fundamentals what we are going to learn. And we also note that since this nanoelectronics, nanoengineering is a broad interdisciplinary term, so we try to make at Amrita, what we do is we offer courses focused on these areas just to make sure what is happening at the fundamental level. So don't be in a situation that, no, I'm from chemical engineering, I'm from bioengineering, how can I do that? No, we have focused coursework that gives you right knowledge about the nano structures, nanomaterials, nanofabrication, and nano design. So this is all about theoretical part. Now, because you are doing masters and PhD programs, we want you guys to do the things, not just listen to the things. So when you are going from printed circuit board to nanoelectronics, from PCB to the chips, the size is decreasing. But with this increase in size, what is happening? The functionality is increasing. Say, for example, I think most of our grandparents used phone, which is like a dial-up phone. And then the digital phones came. Now you guys are using smartphone. I'm guessing some of the students are even texting now. So you're doing multiple functionalities within a smaller device. This is great. But at the other end of the spectrum, look at the complexity. How do you make things at such a small scale? How do you design them? How do you fabricate them? How do you characterize them? How do you test them? And how reliable is this? This is where we are focused with hands-on laboratory experience, where our students who join here will get hands-on experience right from the design to the testing. And we make students do on their own, and we use state-of-art nano facilities in all four aspects. Just to give you some simple examples. So what do I mean by design? So design is once you sit on a software and design a circuit. Design a circuit of transistors, resistors, capacitors, or anything what you want on a software, just make it. And then designing is one aspect, and then go into the lab and make it. And here is a simple CAD design. I just showed you a grid of 20 micron grid array. And again, please remember 20 micron is approximately equivalent to the size of the width of the human hair. So we backslide, please.
Okay.
Back. Yeah. So the left side is the actual software design that our first year students did. And they went into the lab and see how good the replication is. It is like pinpoint accuracy we got at 20 micron things. So this is the state of art what we are talking about. Next. So, okay, now that you made it, we are saying this is nanofabrication, but our eyes cannot see what is happening at there. So this is where the advanced state-of-art nano facilities come in, and we use advanced scanning electron microscopes to see what is the physical size. And you can see in that particular box, you can see 8 microns, 12 microns, 11 microns. These are the physical separations between two things. Next. See, one of my first year students was very, anxious, and he wants to make things. So I just asked him to say, hey, go to the lab and make whatever you want and see what is this. He just wrote the name of our university in nanofabrication. If you can make this,
letters possible, you can make any electronic circuit possible. That is what we want to show here in this particular presentation, that students can go into the lab and do whatever you want under the guidance of experienced faculties. That is with respect to nanofabrication. Well, now when things are going nano, smaller, things drastically change. Or you have many advantages. I'll give you a simple day-to-day example. You all know Digen tablet. You just take the Digen tablet, put in the water, you get these bulbs. Now there is another company called as Eno. Instead of a single Digen, what they did is they made it powder. Now the buzzes increase, and then they say that in 6 seconds your gas trouble is gone. So what they use? They just use nano. They increase the surface area. With the increase of surface area, the reaction time increases. As the reaction time increases, your gas would be, that problem would be solved. The same thing will apply in, nano materials. Say, for example, here I'm showing you some of the examples of silicon, which is a common semiconductor you can make in circular donut shapes, and TiO2, which is an insulator, you can make it in yarns, which is used in sunscreens, and then copper oxide, which is a P-type semiconductors. If you want belts, we can give you belts. If you want fibers, I can give you fibers. Next, gallium nitride, which is an LED used mostly for LED applications, which is a semiconductor. Next, and indium oxide, which is a transparent conducting oxide. At this moment, you are using it. You don't know you are using it, but you are using it because it is a transparent conducting oxide, which is mostly used as a touch screen thing. Okay, now I have shown you design characterization. Now finally we need to test it, right? So I'm just giving you one simple application of a photo sensor, which is the simple operation is this particular material. When you shine light on it, its current increases. And this is a simple device. In the inset, you can see is a simple photo sensor made by the students in the lab. And you can see a simple graph which shows on the x-axis you have time. As with increasing time, on the y-axis you have current is coming to low and going up. Whenever it is low, that means light is off. Whenever it is on, that is current is increasing. So with increasing light, the current is increasing. Now you take an ammeter and measure this current. That current tells you how much of light is being input on a particular device. So these kind of the applications you can make in lab. Not only this photo sensor, there are many applications of nanoelectronics. Say for example, in optoelectronics, memory devices. We started with floppy disk. Now you have 2 GB, 4 GB, 18 GB, 16 GB, 32 GB, 64 GB, all in your pockets. Display technologies. The current buzzword is variable and flexible devices. You can make everything small, at the same time flexible with nanoelectronics. Next. Smart sensors, as Damodaran sir was saying, everything connected to heart, our body, health monitoring, IoT sensors, all these sensors can be made with smart sensors. Next. And energy technologies, as Dr. Senthil sir has already showed you what is this. Okay, this is all good, but where are we in terms of, where is nanoelectronics in terms of India? Traditionally, like conventionally, we are mostly on the edge of designing, VLSI designing, but India has, next. Yeah, India, right after the COVID, we suffered a lot. Along one of the major unit that suffered is the complete manufacturing in almost all the countries has been halted by the shortage of chips. That means there are no enough chips to supply the entire world. So that's where India has realized, okay, we need to do something. So you can see the government is stepping up and making, efforts and giving subsidies to these chip manufacturing companies to come to India and establish their companies. And one of the primary focus point of the government is manpower is shortage in this particular area. There are more of design guys, less of manufacturing guys. So we need to level it up. So that's where you can see in the March 2024, very recently, India started 3 manufacturing companies, one in Assam, 2 in Gujarat. And the other news, very recent, May 8, Tata Electronics has started already making the chips, and they're also exporting them from India to the other countries. So with this, I hope I have given you an overview of what nanoelectronics is, where it is, and where are the job companies, and you can see the list of job company this. And I believe you guys would be at the right time, at right place to focus this nanoelectronic course. I will see all of you in the labs very soon. Thank you.
Thank you, Dr. Lakshman, for your presentation. Before we come to the end of our session, I'm happy to invite Dr. Binita, who is a former student who did her master's and PhD at our Amrita School of Nanosciences and Molecular Medicine. She is now a very successful manager in the R&D sector at the Hindustan Petroleum Green R&D Center, HPCL, Bangalore. Over to you, Dr. Binita.
Thank you. Can you please confirm whether I'm audible?
Yes, ma'am, you are.
Thank you. So, respected Dean Dr. Shantikumar sir, esteemed very own PhD mentor, Professor Damodaran, distinguished faculty members, Dr. Senthil and Dr. Lakshman, and all dear attendees, I extend a warm good evening to all. So, this is actually a proud privilege to be a part of this forum. So that at least I can share my experience as a student in exploring the wonders of nanotechnology at Amrita School of Nanosciences and Molecular Medicine, Kochi. So with the presentations which has been carried so far, I hope you all had a glimpse of the emerging trends and the career opportunities in the field of nano energy and nanoelectronics. So before sharing my experience, I'll give a brief about my background. I'm Dr. Binita. Basically, I'm a chemical engineer, and I did my BTech in chemical engineering from TKM College, Kollam. Then I pursued my master's in nanotechnology at the same center, which is Amrita. And with that experience, I was being selected as a junior research fellow at the Indian Institute of Science Education Research, ISA Trivandrum. And further, I have decided to pursue my PhD back again at Amrita. And currently, I'm working as a manager at Hindustan Petroleum Green R&D Center, Bangalore, which is actually a part of the public sector enterprises undertaking, which is an oil and gas company, which you all might know, HPCL. And completing my master's and PhD at Amrita School of Nanosciences and Molecular Medicine was literally an incredible journey. And I want to share what made it so special in the hopes of at least inspiring a few of you as you might consider your own educational path. So just like the presentation has been discussed, there are many highlights for this center. And for the benefit of time, I would like to mention a few. So as a student, first and foremost, what I felt is the state-of-art facilities which Amrita has. So you already would have got a feel of the facilities from the presentations being shared. You will definitely, as a student, will have hands-on experience on almost all these facilities, which made our experiments and also the research so easier and also much exciting. Well, the next point which I want to mention is the engaging curriculum. So typically the curriculum will be, at times it will be updated, but in Amrita, the curriculum was designed to give us a strong foundation in the field, while again allowing us to explore our own interest through some selected electives also. So what this professors has done is they have made this material very interesting, and also they continuously update it, often incorporating the recent development in the field of research and development, which actually, in other words, keeps us almost engaged and motivated to learn more. Well, the next point, or the third point which I want to mention is the supportive mentors. Being in front of my very own PhD mentor, Dr. Damodaran, I can undoubtedly say that you will definitely get the best professors which you can get in the field. And these professors were not only knowledgeable, but they also genuinely care about our success. They always be available for help, no matter whether there is in the field of coursework, any offer advices on your research projects. Even they can even guide us through our academic and also personal career decisions also. So their support and their encouragement made a huge difference in my confidence and development, especially as a student and even also as a researcher. So the next point which I want to mention is actually the research opportunity. Well, see, as you could see, the curriculum of this master's program is actually organized in such a way that you have a complete year dedicated for conducting research. That is a rare opportunity. Typically, many of the universities won't allow you to have such a long span of research experience. But here at Amrita, you guys are encouraged to work on some challenging and areas. You can think creatively. You can tackle some important problems that will definitely be supported by your providing resources and supports, just like fundings, access to advanced equipments, or even it could be a collaborative project with some industrial partners. And I would like to add, my PhD was actually supported by ISRO, and along with that, I have been funded through DST, some programs also. So further, additionally, you might even get opportunity to find or present your works at international and also national conferences, which also definitely benefit your career, and definitely it benefited my career. So in short, studying at Amrita was literally a life-changing experience. They have excellent facilities, excellent faculties, engaging curriculum, then exciting research opportunities also. So this actually put a strong foundation in my research career so that I can get a path towards my industry. So if you are an undergraduate who is considering for your next step, or even a postgraduate who is interested to pursue your PhD program, I highly recommend the Amrita Center for or School of Nanoscience and Nanoengineering for your upcoming studies. It's literally a fertile place where you can definitely grow, you can learn more, and you can even achieve your dreams. So I wish all of you a great success, and I appreciate your patient listening. Thank you.
Thank you, ma'am, for sharing your experience with us. I hope it motivated the students who are looking forward to join our institute. With that, we come to the end of our session. I would now like to open the floor for the participants to ask the questions to our eminent speakers here. You can either click on the raise hand button or you can type in the question in the chat box so that we can read it out.
Any questions, any clarifications that you need about nanoelectronics and nanoengineering at Amrita, we would be happy to answer.
So there is one question directed to Dr. Damodaran. Could you please give me an idea about what are electronic devices and do they have any applications in biology?
Yeah, so basically we are developing, nanosensors for different medical and healthcare applications, because there are a lot of, being in a hospital campus, but doing nanoelectronics or nano energy applications, there are a lot of devices that we make which are meant for medical applications. Typically, for example, some of the, 3D printed micro devices that I mentioned about sensors or, batteries that can actually power, micro medical devices, and which are basically very important, and it is one of the hot topics in today's era of nanoelectronics and nano energy or nano engineering applications. Yes, we do typically sensors which can be for multiple applications, and it can be integrated to have multifunctionality, and it also be self-powered because we could have a battery printed along with the medical device itself. So that's the kind of thing. And there are also a lot of other applications in terms of, for example, medical devices which could be implanted into the human bodies, where the the devices have to be covered with certain kind of coatings because of the pH values of inside the human body with the blood and all other stuff. So there have to be some kind of coatings to maintain the device structures and things like that. There are also a lot of other bio applications our biomedical team is actually working on. So we do collaborate between the nanoelectronics, nano engineering, and bio a division of our school.
So we have another question. This is a student who has done his BE in ECE department in Vailtech Multitech. Sir, what are the softwares that are currently used in industries for nanoelectronics devices?
Hello, Santosh. That's a very good question. So currently people are, in terms of simulations, people are using, start with LT-Spice, H-Spice, and they go up, and then you have Cadence, which can, give all the advanced tools at the nanometer level to design the circuits, validate the circuits, test the circuits. This is just with respect to the circuit designs. And on the other hand, in terms of nanoelectronic devices, you want to understand how that particular material works at the nano level. There you use DFT calculations and VESPA tools to get an overview of how a material works at the nanoscale by shrinking its size and mimicking the practical situations within the laboratory or within the computer setup to get a pre-knowledge of how that material works. And then they just take that knowledge into the picture, go into the lab, make it, and see whether it is performing, how it is performing in terms of efficiencies and reliabilities.
Thank you, sir. There is another question from a BE student. Could you please explain the connection between electric vehicles and nanotechnology?
Yes, electric vehicles, for example, we are talking about which are basically operated by lithium-ion batteries. So typically, one of the examples that Dr. Sendil highlighted is also that you want to be charging, let's say, the batteries in 5 minutes, like something equivalent to that of filling, petrol or diesel in the cars. It has to be that fast. So that kind of batteries are enabled only by nanotechnology. And that's one simple example to say about electric vehicles. But electric vehicles involves a lot of other components in terms of, for example, the DC motors which are required could be nanotechnology based. It could be the battery management system based on nanoelectronics and power electronics, right? It could be the thermal management of the electric vehicle batteries, for example, to keep it cool and safe. There are a lot of situations where nanotechnology comes into picture when you are talking about electric vehicles.
Thank you, sir. The next question is, kindly tell us about what about metal oxide nanoparticles that have a role in nanoelectronics?
So that's a very, very good question. Metal oxide nanoparticles. Okay. To be specific, what metal oxide I would ask, but let me give you a general answer. Say, for example, gallium oxide, that is a metal oxide and it has a wide band gap material. So whenever you have materials, this wide band gap material, you can use it for UV photo detection applications, where recently with the COVID surge, everyone is interested with this UV based detectors and UV based sensors. So that and the next one is indium oxide, metal oxide nanoparticles. These can be used. These are basically insulators, but you can dope them or nano engineer them to induce conductivity into them. And one other important thing is these metal oxides are transparent. So you can use them as transparent conducting oxides for, cell phones or, any display based technologies. And
Thank you, sir. The other question is, what are the advantages does an analog engineer have when he switches his career to nanoelectronics, and what are the commonalities between both the fields?
okay, so in terms of analog engineering, I'm guessing you might have an extensive knowledge on how a BJT, bipolar junction transistor, works. The same thing in nanoelectronics, it's not only limited with digital electronics, it also has these analog components in them. So your expertise or your pre-knowledge on analog engineer would greatly help you to have an excellent career in nanoelectronics. At the end of the day, both of them deals with both the nanoelectronics and your analog engineering field deals with how you can modulate the charge of a particular device. It might be a transistor, it might be a field, it might be a bipolar junction transistor or a field effect transistor. How you can modulate at the atomic level the charge, the mobility, or how can you make a device more faster and smaller in size. I hope this answers to your question.
Thank you, sir. We have one question directed for Dr. Sendil. What is the scope in energy area, and what specifically will we be learning in the labs, in particular to this field?
So, as I mentioned, in 4 different fields in engineering aspect, we are mainly focusing on thin film solar cells, particularly CDT based thin film solar cells, which can be a futuristic as alternative to the silicon based solar cells. That can be a very good topic we are already working on. And as I mentioned, in the high power batteries, like where nanostructures can play an important role in bringing some high power batteries. And as well as my main focus is on the sodium ion batteries, so where it can be alternate to the lithium ion battery. So it's not like for electric vehicle application, but I can use this for the stationary applications, let's say as a UPS battery or some other stationary application. So we are working in multiple energy based applications, and we are also looking for the photoelectrochemical water splitting or catalytic water splitting, like that. Much futuristic applications also we are looking for.
Thank you, sir. We have another question directed to Dr. Nair. Is the field of nanoengineering and nanoelectronics an upcoming field, or is it an old one? Does it have immediate future, or is it the new field that is taking off?
Well, electronics and engineering, of course, as you know, is an old field. There's been a lot of developments in it. Nanotechnology, what we are talking about here, is an enabling technology. How do you reduce the scale so that you can improve the performance, improve the efficiency, improve the size, improve all the parameters of functionality? And in that sense, it is a relatively new field. It's an emerging field. There's still a lot of developments. But if you look at the various technologies that are already in the market, don't think that this is something that has just started yesterday. It has been maturing, it has been growing. There are a lot of nanoscale engineering and electronic devices already in your automobiles, or they wouldn't be functioning. It's not like in the old days. If you look at any basic devices, I think, has been pointed out by Dr. Lakshman, if you look at your TV screen, your smartphones, all of them are already using nano-enabled technologies, reducing the size, increasing the functionality. And so it is a field that is not necessarily new. I would not call it new, but it is recent. I think I would say in the last 10 to 15 years, it has grown substantially. What is important to keep in mind is that it is rapidly developing. A lot of new companies are coming into the market in India. And I think what is important for you to understand is that in our country, we are starting to develop our own products, exporting them, as Dr. Lakshman said, Tata is exporting chips. And so that's something to keep in mind. This is a time that we should be getting to be comfortable with and knowledgeable, and also with respect to techniques and laboratory techniques and manufacturing techniques, we should be comfortable with the new technologies so that we can, explore new avenues for our career.
Thank you, sir. We have another question to Dr. Nair. Is it necessary to learn the quantum physics at more of a deep level to adapt from microelectronics to nanoelectronics?
Well, we have quantum physics. It's, of course, an important aspect of nanotechnology, because already, if you're looking at microelectronics and if you're looking at macroelectronics, there's not a whole lot of applications of quantum theory. But when you get into nanoscale electronics, you absolutely have to understand that the phenomena and the magnitudes of the phenomena and all are related to quantum theory. Ballistic transport through nanowires is a quantum phenomenon. So change in your energy levels in nanoscale systems is a quantum phenomenon. So it is important to understand that once you start getting into the nanoscale, you are also getting into the quantum scale. Of course, today, if you ask me about as well. But putting that aside, quantum physics is obviously a part of nanoelectronics and nanomaterials, and it is part of our course as well.
Thank you, sir. The next question is, which nanoparticles are widely used in nanoelectronics, especially in electrodes preparation?
To answer that question, there's not specifically one specific nanoparticle that you want to specify, or one nanomaterial that you want to specify that is, very important, because you can imagine from, the materials band gap point of view. So for different kind of applications, you might need different kinds of band gap of materials. So typically it would depend on what exact application that we are talking about in terms of, nanoelectronics. So there are a wide range of applications, and currently the most trending thing is basically to do work with 2D materials, right? So which has a tunable band gap when you change the number of layers of the 2D materials and things like that. So that's becoming one of the important materials as far as nano or optoelectronic applications are concerned. Any more?
Just as sir was saying, there is no specific material. You look into what is your application and what are your requirements. See, when you talk about an electrode, it's not a simple electrode. You are putting electrode on a material. So when you're putting that electrode on a material, you're forming an interface. Then you need to study the compatibility of that chosen nanomaterial or nanoparticle with respect to the existing material. So all these things come into picture when you're actually making a reliable device. You need to look into the interface band alignment. You need to look into the compatibility. You need to look into the cost aspect, because at the end of the day, you want to make a device and sell it out. If you make a device that is costing lakhs and lakhs of rupees, nobody will gonna buy it. So then you need to compromise on the quality, but at the same time look for alternate nanomaterials which give reasonable performance and you can sell out reasonably. So it's not like in single, we cannot give you a direct answer, hey, go take this. It depends upon many factors that you need to consider in making these electrodes for nanoelectronic devices.
Thank you, sir. With that, we come to the end of our session of today's virtual webinar. I really thank our eminent speakers for taking time and interacting with you, and also our participants. A special thank you to Dr. Binita for giving us an overview about her experience at ASNSMM. Thank you all. We'll hope to see you soon in our campus. Thank you.